Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, go ahead and hit the subscribe button because you are in the right spot. Let's go ahead and get into the current video. In this one, I want to take a look at what's called a homotopy relative to a subspace. And I'm going to go ahead and assume that you are familiar with the concept of a homotopy from a previous video. Let me set up the idea for homotopy relative to a subspace. So let's say I have the following. I've got a path F, and I've also got a path for G. Now let's say this path G has the following property. It actually matches up with F for a certain stretch of time, and let's say that consists over is contained, of course, within a subspace A. So in other words, all through the paths F and G overlap within this subspace A. And then when I do a homotopy from F to G, let's say, of course, the homotopy, the one parameter family of maps, is always the same within that subspace. This is the idea behind a homotopy relative to a subspace. So I'm going to go ahead and then give a formal definition for this. So suppose H is a homotopy from F to G, and there is a subspace A for which the following happens. H T X is equal to F of X, which is also equal to G of X for every X within the subspace. So in other words, the homotopy is fixed on this subspace A. Then we say that F and G are homotopic relative to A. And write one of the following. There's a couple different ways that we can denote this. Probably the most common way is to write H, F, and then use the sort of equivalence relation symbol with the subscript A, G. And this, if you see that notation, means H is a homotopy between F and G relative to the subspace A. Of course, we can also write H is a homotopy from F to G, and then you might say like relative to the subspace A, something like that. I'll probably use both of those notations depending on the context, but it means the exact same thing. All right. Now, one of the most important types of functions between topological spaces that we are going to then consider throughout these discussions is something I've already mentioned called a map. But let's go ahead and give a definition for what a map is. Or I'm sorry, a path. A path in a topological space X is an element of the continuous functions from 0, 1 to x. So it's a continuous function from that closed interval 0 to 1 to x. And let's consider and then one more definition to tie along with that. A path homotopy is a homotopy relative to the boundary of that. Let me illustrate what that means. Okay, so let me give a picture for what a path homotopy is. So, right, a path homotopy is a homotopy which is relative to the boundary of I. And let's say I've got the following picture. Okay, this is going to be the path F, and then if I was to take another path, the same endpoint, and come down here, this would be G. Then a path homotopy means it's going to leave the endpoints which match fixed, but it's still going to transform F into G continuously. So I'm going to have this one parameter family of maps that is going to transform F into G, but it's going to leave the endpoints fixed. And this is going to be what's called a path homotopy. And again, notation for that is we could say that H is a homotopy relative to the boundary of I to G. So F and G are homotopic relative to the boundary of I via the homotopy H. Now I'm not going to prove this because it's basically the same thing that I proved in a previous video, but path homotopy is an equivalence relation on continuous functions 0, 1 to x. In other words, path homotopy is an equivalence relation on the paths in a topological space. Okay? Again, this is going to be an important concept going forward in these videos. Thank you for watching. Please consider subscribing.